Okay, today we'll start with related rates. So let me explain what a typical related rates problem is. Okay, so a typical related rates problem, you start, so a typical problem okay, so first there is a story. Okay, so this is in words. Okay, so somebody buys something, somebody is running away from somebody else, etc. Translate this to, so the important part is this part. Translate this to calculus. Well, for related rates problem, typically you will obtain something like this. Okay, so for related rates problems, a typical formulation is like okay, so you have several variables, f of t squared plus, I don't know, ft gt equals constant, say. Okay, so it will be more complicated than this, but there will be several things changing in the problem. You will denote them by some functions. And this, when you read the story, there is a relation between them. Okay. And here, so let's say this is A. Take derivatives of both sides. Both sides. So let's say in this, let's continue with this. You will have 2 f of t, f prime t, plus f prime t times g of t plus f of t, g prime t equals 0. Okay, so this is for related rates. This stage is again typical. After you establish the relation that's narrated here, you get an equation, and you take the derivative of both sides, you obtain this. Okay, now evaluate this at some point. Okay, so suppose we evaluate this, take derivative of both sides, and evaluate at the given time, say t sub 0. So let's put t sub 0s here after you take the derivative. Okay. So most of the time t sub 0 will not be explicitly given, but the story will say, at the time when something is happening, what is happening to the other thing. So that means you explicitly evaluate everything at a certain time. Okay, now you read again the story. There's the story. And you notice that all of these numbers are given except one. Okay, so you have this number, this number, this number. Well, that's already given here. Okay, so this number is already given, and this number. Okay, read the story again. Okay, so the story gives all these numbers except one, and asked for that one. Okay, so solve the problem. So solve for the remaining one value. Okay, so you solve the calculus problem. But now answer, there's a story, say, with a question. Okay, so finally answer the question in human language. Okay? So, for example, if this says how fast is something is changing, and you say theta equals pi over 2, that's not the answer. Okay? So, you have to go to the story, understand what is asked, and then here say, when those things are happening, the thing that we are interested in is changing at a certain rate. Okay, so that's the answer. When here you find that t equals 5 or g prime equals 7, that's not the answer. That's the answer to the calculus problem. Okay, you translate to this calculus, and okay, so let's say this is the C part. You solve the calculus problem. Okay, so this is important. In particular, in the exams, you more or less do this, and here you have some value. It turns out that in the human language, the number 5 will pass, and you have 5 somewhere here. Okay? Then you come and object to your grading, and you ask for extra grade. You don't get any extra grade. Okay? So the reason is this. Okay? So this is what happens in real life. There is a question. Nobody cares whether you solve it by calculus or by looking at your friend. Okay? And the answer is important. Okay, let's start with doing some simple examples. Okay, no matter how complicated the story is, this is how you solve a typical related rates problem. Okay, after you translate the story, you must have an equation like this, involving all the values mentioned in this story, and invariably the story is talking about rate of change of something. Okay, so you need this part. When you come here, you realize that all these numbers are given, except one of them. Okay, then you solve it. Okay, so let's see. There are some problems that you want to solve in every section, and after that, I'll go and I'll solve the problems at the end of the section. So, so for example, let's look at this one. Okay, so one. So what is the volume of a sphere? Yes, volume is, okay, what's the volume of a sphere? Hmm?
4 by r cubed.
Mm-hmm. That's the surface area. Divided by 3, you get the volume, right? 4 over 3 pi r cubed. Okay, so we So we assume that in related rates problems, for example, this volume is increasing. Okay. So you are inflating this balloon. It's inflating. So radius is changing and volume is changing. Okay. So assume V and R are functions of time. For example, when the volume is increasing, okay. So actually you have volume, which is a function of time, is 4 pi over 3 r of t cubed. Okay, so let us not ask the story yet. We are trying at this point to see the mechanism of related rates. Okay, now take derivative of both sides. So somehow we read the story, we translate it to calculus. It involves the volume of a sphere. Now we are here. We take the derivative. Okay, so take derivative. So v prime t is equal to 4 pi r of t squared r prime t. Okay, so evaluate it at a certain time. Okay, now the story will give you one of these things, or two of these things in our case. Okay, so you have this, you have this, and you have this. The story, for example, may say how much the volume is changing when the radius is changing at a certain rate. Okay, so you look at the problem, that's not enough. Okay, because here we have three variables. If the story gives you only this value and asks for this value, it's not well defined. Okay, at every instant the volume is changing in a different way. Okay, even if the radius is increasing constantly, because every time R changes and it changes the way the volume is changing. Okay, so of these three, two of them must be given in the story. Okay, so for example, so how much the radius is increasing when the radius is I don't know 5 centimeter and the volume is increasing at 7 centimeter cube per minute. Okay, so let's make it slow. Okay, so of course this story comes before this, but this is actually how you create related race problems. First you play with the formulas and then you look at this formula. Okay, so let me decide to ask one of them. In this case, we decided to ask this one. Okay, so we have to supplement numbers for these things. Okay, so when we take this, we write this here now. So V prime, how much is the radius is increasing? Volume is increasing at 7 centimeter cube per minute. This is equal to 4 pi. Radius is 5, so this is 5 square times R prime. Okay, let's leave it as R prime. Okay, so maybe here I should also write, since I started to write the units, this is 5 centimeter. The radius is 5 centimeter. I'm taking square and R prime. Okay, so you see that R prime is already there. Centimeter squares cancel. So R prime is equal to 7 over 25, 100. Okay, so 100 pi centimeter per minute. Okay, so R prime is this. But R prime is 7 over 100 pi is not the answer to this, because you see in the story there is no R. In the story saying how much is the radius increasing. Okay, so now your answer should be, if you want to give a short answer, you can just refer to this at that time. Okay, so answer at that given time, the radius is increasing at a rate of 7 over 100 pi centimeter per minute. Okay, so this sentence is particularly important when you get minus here. Okay, then R prime is equal minus 7 is not the answer to the question. You must tell what is happening to R prime. Then you will say at that given time the radius is decreasing. Okay, because minus in derivative means the function is decreasing. Okay, at a certain it is decreasing at this positive number. Okay, so minus is taken to decreasing. Okay, so this also tells you how you cook up related race problems. You find the relation, take the derivative, and then decide which one you will ask. So you supply all the other numbers, and then you write a long story how this interesting situation came up. Okay, so let's do another simple one. Let's first do simple ones, then bit by bit we'll get more complicated. Okay, the second one is the following. Okay, so this is the simplest thing. So maybe I find the wording here. Okay. So I'll write the long story here because that's very typical of related race problem. The lengths of the sides of a rectangle are changing as functions of time. Okay, so find the rate of change of the area. Find the rate of change of the area of the rectangle with respect to time. At the moment when the length of one side is 2 meters, so this is a huge rectangle, and decreasing at the rate of 3 meters per second. So after half a second, the side is gone. Okay. And the length of the other side is 5 meters, and the length of the other side is 5 meters and increasing at a rate of 4 meters per second. Okay, so this is the story. Okay, so this is a calculus problem. So first we translate it to calculus. We are talking about the area of a rectangle. Okay, so it always helps if you draw something for yourself. Okay, so here, so let's say solution. So first translate to calculus. Okay, so we have a rectangle. Let's give names to the sides. Okay, x, it's changing by time, so x of t, y of t. So area of this rectangle is x of t, y of t, area of rectangle. Okay, so this is our first equation. Now we take the derivative because in the story rates of change are given. A prime t is equal to x prime t y of t plus x of t y prime t. Okay, so at a given, now we look at the story, all of these numbers are given. Okay, rate of changes are given, the actual lengths are given, and the rate of change of the area with respect to time is given. Okay, so the rate of change of area with respect to one of the sides is different than the rate of change with respect to time. So that's why the story has to tell you what is happening. Okay, so at that given time, at that given moment, okay, a prime t, okay, so here, since I mentioned that I am fixing time, I don't write t sub 0. I can write t sub 0 because it's clear what I'm doing. This I don't know. X of t is, okay, let's say it is this part, is 2 okay, let me drop the units now. it is 2 meters and decreasing at a rate of 3. So it is decreasing at a rate of, decreasing means minus 3. And the length of the other side is 5. No, I put in the wrong numbers. Okay, so x prime is this one. So not to get confused, let me write this. X prime is 2. Okay, x prime is 2, x is 2, y is 5. Okay, so let's. Okay, now x prime is minus 3. Okay, and y is 5 plus x is 2 and y prime is increasing, so this is 4. Okay, so this is minus 15 plus 8 equals minus 7. If you put units here, okay, so this is centimeter per second, meter. Okay, so this is meter square per second. Okay, so the answer, okay, at that moment, okay, because it's asking what's happening at that moment, the area is changing, is decreasing. Okay, since I have 7 here, minus 7 here, is decreasing at a rate of 7 square meters per second. Okay, a very simple problem. I did it in detail because no matter how complicated the problem is, you will do exactly the same thing. Okay. I drew a picture so that I can visualize what's happening. Okay. I gave names to the size of this. The area of the rectangle is mentioned here, so I write a formula for the area. Rates of change with respect to time is mentioned here, so I take the derivatives. Okay, so at this point now I go back to the story and plug in all the given values. Okay, it's a nice cooked up example, so all the numbers are given except one. I solve for that easily and I get this. Okay, so this solves at this point. The calculus problem is solved. Now we go back to the problem and what is asked. Okay, find the rate of change of the area. Okay, at that moment the area is decreasing at a rate, since minus, I put that minus here, decreasing. Okay, so it's easy to explain this on simple problems. This goes to decreasing here, and this 7 goes to here. Okay, so in everyday life we don't say the area is changing at minus 7 meters per second. Okay, among technical, when you are in a technical team, that's what you do, of course. But when you are talking about your result to a common audience, you have to use everyday language. Okay, any questions so far? Okay, so let's get a little bit more complicated. Okay, so another typical problems with the related rates is a ladder leaning against the wall. Somehow it slides. Before somebody falls off and breaks his leg, we have to measure how fast it is sliding away or how fast it's going down. Okay, so that's the next typical thing. So again, I'll write the exact wording of this. Okay. A 3-meter long ladder which is leaning against the wall. Starts to slide away from the wall. Okay. If the bottom end is moving with the speed, if the bottom end is moving with the speed of 5/4 meters per second at the moment when it is 2 meters away from the wall. Okay, so how fast is the top end is moving at the same moment? How fast is the top end moving at the same moment? Okay. So the answer will be the top end of the ladder is moving down at a certain rate or moving up. Well, in this case, it doesn't move up, but suppose it was moving up. Okay, so if this was, instead of this ladder sliding down, you could be pushing the ladder towards the wall, then the top end will move up. Okay, so whether your calculus answer comes up plus or minus, you have to translate it to what the top end is doing. Is it going up or down? Okay, so in this problem, of course, the top end will go down. Okay, and since it will be the rate of change of the height of the top end, in the calculus problem, we expect to find a negative number. Okay, so in the answer, that negative number will translate that the top end is moving down at this rate. Okay, so these are our expectations before we start the solution. So this ladder problem is very typical. So you see the ladder is leaning against the wall, the length of the ladder, the height of the ladder, and of course if these two are given, the distance, the bottom of the ladder from the wall, these are three numbers. Most of the time, two of them is given, you find the third one. Then you take derivatives of this right triangle. Okay, so that gives you how fast these things are moving. The length of the ladder, if it's not plastic, is not changing. So if you take the derivative in your equation, the length of the ladder is constant. The derivative is 0. So the height of the ladder and its distance from the wall are changing. Okay, so you have these unknowns. How fast the bottom is moving, how fast the top is moving, okay, and the lengths of those two sides. Okay, so at least three of them will be given, and you'll solve the other one. Okay, so again, let's say solution. So again, draw a picture. Put your okay. So this length, let's say, is x of t. This side is 3 meters long. Okay. Since this is perpendicular, I know what this side is. It's not given, but I can find it. Okay, so that is 9 minus x squared. Okay, so this is square root 9 minus x squared. Okay, so it is plus because I'm taking distance. Okay, so this is the situation with the ladder. And the story says that it is moving at a certain rate. Okay, so this thing is 5/4 meter per second when this thing is 2 meters. Okay, so when this is 2 meters, this is square root 5. Right, so in parentheses, I have this. I know from the picture that if this is moving this way, it will move like this, and this is what is asked. Okay, so this is how I use my picture. Okay, so now I have to write these things. Take derivatives. Okay. And okay, so maybe I can give this. Okay, so let's call this y of t. Okay. So I have the relation I have between x and y, because this question is what is y prime? Y prime is what? Okay, and this is x prime. Okay. At a given moment, you see 3 square root 5, 2 are given, x, y are given, x prime is given, y prime is asked. Okay, so from the figure, we have x square plus y square is equal to 9. Okay. Now take derivatives. So we are again, we managed to write the first equation. Rates of change are mentioned, so we take the derivative. Take derivatives. So 2x x prime plus 2y y prime equals 0. Okay, so the length of the ladder is fixed. Okay. Now put in the values. Okay, simplify. I don't like, nobody likes these 2's here. This is optional. Simplify. Optional. Okay, so x prime plus y prime is 0. Plug in the values in the known values. Okay, so at that x is 2, x prime is 5 over 4, plus y is, okay, I solve this here. I can solve it explicitly somewhere. Sometimes it's not easy just by looking at the picture. Sometimes you have to solve it. Okay, so I found when this is 2, this is square root 5. Y prime, I don't know. Okay, fortunately, 0. Okay, so at least one of them is unknown. Now solve for the unknown. Okay, everyone agree? Objections? I hear objections. You want a plus or minus somewhere? Okay, so y prime is equal to minus 5 over 2 times divided by square root 5. Okay, so this is minus square root 5 over 2. And I can now put the value, units here. Everything is meters per second. Okay. Okay, so we didn't answer the question yet. We solved the calculus problem. Okay, so answer. So I'll do the same thing here. Okay, at that moment. Okay, so since the story says at that same moment, let us be funny and use the word same. At that same moment, the top of the ladder is sliding down at a speed of square root 5 over 2 meter per second. Okay, so this is the answer. Again, let me mention once again that this minus I interpreted as sliding down. Okay, so, and this number here I gave as the raw speed. Okay, so this is what is expected in the answer. Okay, from engineer to engineer, scientist to scientist, you can say that the top of the ladder is moving at the rate of minus square root 5 over 2, and everybody understands. But normally, when you are writing a report or explaining it to a customer, someone with lots of money who will sponsor your project, okay, so they don't want, now you have to explain everything in detail, okay?
I have a question. We took the derivative of x and y with respect to what?
Time. Okay, so thank you for that. Let's mention, so derivatives are with respect to time. Okay, so maybe you mention it here. Okay, since the speed is given and this is meter over second, so we understand that it is derivative with respect to time, but in the solution we have to mention that technically we are taking derivative with respect to time. Okay, so let's see. Another familiar, very famous midterm question is an upside-down conic water tank. Water is either pouring in or pouring out. Okay, so water pouring in means the volume is increasing. Water pouring out means the water is decreasing. So you take the derivative of volume. It is either plus or minus depending on whether you are pouring in water or you are letting water out. Of course, since this is not cylindrical, it's conic, the water level changes as the height changes. Okay, so all these things are related to each other. There is also a Thales theorem used somewhere. So it's a very popular problem for midterms. Okay, so solve a few problems like this before the midterm. So let me erase this one now. A water tank has the shape of an upside-down cone. Okay, so this is very typical. A water tank has the shape of an upside-down cone. Okay, now we have to give the dimensions of the cone. Okay, so this is going to be crucial in finding the relation between height and radius of the water cone. With radius 2 meters and height 5 meters. Okay. If the water is running out of the tank at a rate of 3 cubic meters per minute, when okay, so the rate at which the water runs out, if it is not being pumped by a regulated machine, then the rate changes on the height of the water, right? So we have to tell at which time this is happening. When the depth of the water in the tank, depth of the water in the tank is 4 meters. Okay, so if the water is running at this rate, when the depth is this, find the rate at which the water level is changing at that moment, or at this moment. Okay. So water level is height of the water at that time. Okay. So again, in the solution, I draw something to help me. Okay, so water tank is something like this. Well, this is a calculus tank. I have a tank in my garden which doesn't look like this. Of course, when you are constructing a tank, normally there are lots of other parameters. You want it to stand on its own weight with minimum amount of material used, etc., etc. Okay? So generally the shape of tanks is not regular, because if it is regular, it bounces, it collapses. So you have to give some inward and outward curves there. Okay, but this is calculus tank. It is like this. So this is radius. This part is 2. And, okay, so this part is 5. Okay. And then we have a different consideration. There is water here. Okay. And this height of this water, 4. This is 4. Okay. And water is pouring out at 3 cubic meters per minute. Okay, so now that I started to write units, this is 4, this whole thing is 5 meters, this is 2 meters. Okay, and what is asked? Find the rate the water level is changing. So we want to find how fast this is changing. Okay, so this part, this is going down at a certain rate, and this is what we want to find. Okay, so let us give names to this. At any moment, let us call the height h and this radius r. Okay, so we are in a triangle like this. I'm just taking this part. Okay, so this is r, this is 2. The whole thing is 5, and this part only is 4. No, it is h. I'll find, at that moment it is 4, at h. So this is typically what happens. There is water here. Okay. This is, now I'm interpreting my picture. This tells me how fast the volume is changing, with minus, of course, since water is pouring out. I want to write the volume at a typical moment. Okay, so volume is 1 over 3 pi r square times h. Okay, that volume is changing with respect to time. If I take the derivative with respect to time, it is at that moment 3. That moment is when h is 4. And r, I don't know. But from this figure, I know that I can find r. Okay, so when h is 4, I know what r is. If I take the derivative of the volume involves r and h. So if I take the derivative, the volume will involve r, h, and their derivatives. Okay, so but the derivative of r prime, derivative of r prime is not known. This is asked, but since they are related, I can express the derivative of this also in terms of this. Okay, so then there is only one unknown, h prime. Okay, so I take the derivative of volume. I can write the volume in terms of h only. Okay, because r depends on h. I take the derivative. V prime is minus this number. In the expression, I'll have h squared, h cubed something. The derivative involves h and h prime. H is given. H prime is asked. Okay, so everything is perfect. So it remains now to start the calculus problem. Okay, so now that we solved it mentally, so from the figure, okay, so we have 2 over 5 is equal to r over h. Well, in the problem, we'll have r squared, so let's have r from here. R is equal to 2h over 5. Okay, so volume as a function of time is pi over 3 r squared h. Okay, so I put this inside here, pi over 3, 2h over 5 square h. So let's see, this is 4 pi over 75, right? H cube. Okay, so let me take this to this side. This is the function I have. Now I take the derivative of both sides. Take derivatives. Okay, so v prime is equal to 4 pi over 25 h square h prime. Okay, put in values. Okay, so V prime is minus 3. 4 pi over 25. H square, H is given as 4, so this is 16. And H prime. So you see that now I can find H prime. So what is the answer here? So let me just write the answer. So H prime is equal to, I'll just write the answer here. Hopefully everything works. Minus 75. Okay, so this thing is over here. Over, well, it was easy here. I can multiply this 64 pi. Okay, so and this is now I can put in the units. Everything is given as meter and minute. So this is meter per minute. Okay, so we solved the calculus problem. Now the very last thing that will get us his. No, H prime is.
4 pi over 75, and in the next step it's 4 pi over 25.
What is? So you don't like this part?
No.
Here?
Volume, yeah, the volume is 4 pi over 75, but in that, so we took the derivative, it became 25.
I take 3 down. 375 cancels. You erase my masterpiece here. So what was H prime here? Minus 75 over 64 pi meters per minute. Okay. Okay, now let's write our final answer and take a break. Okay, so answer. At this moment, or rather let's make this meaningful, at the given moment. Okay, so here we use H for height, but height is not mentioned here. This person is thinking about the water level. So at the given moment, the water level is minus decreasing at a rate of 75 over 64 meters per minute. Okay, so let me write this in a readable way so that I get my funds. 64 pi. Okay, so one last second. So again, I emphasize that I didn't say minus in my answer. I interpreted this minus as decreasing, and this raw value here I gave in an understandable sentence. Okay, so typical water tank problem. Okay, let's take a 10-minute break, then we'll continue.